Chapter 11.2 is on series. Now, this is the very first introduction to series, so it is very important to make the distinction between a series and a sequence. A sequence was just a list of a bunch of numbers in order. A series is the sum of them, so you got to add them all up. So partial sums gives you a good idea of what it starts to look like. So these are what your partial sums should have looked like. Down here, the two questions below that were about distinguishing between the sequence converging versus a series converging. In this case, the sequence seems to converge to 0 because each of these fractions starts to approach 0. But the series seems to converge to 1 because the more of those terms that I add together, they seem to add up closer and closer to 1. Now, this is how you would write that if a series were to converge. Now, when is it possible? How is it possible to add an infinite number of terms and have it not go on forever and ever to infinitely increase or decrease? Well, the sequence must start becoming 0. You have to be adding zeros eventually, right? If I want to add up an infinite number of terms here, eventually those terms better start looking like zeros, because that's the only way a series will actually converge. Okay? So then what's guaranteed? But really what it will do, it'll only give me a chance at converging. It doesn't necessarily mean that it will. However, the opposite of that is that if the sequence doesn't actually converge to 0, then the series will definitely diverge. Okay? So this is what we call the divergence test. Okay? This we will be going over much more in class and start to practice, where we take a look at these sequences and to see if they actually converge or diverge to 0 or not. However, what I do want to take a look at to start our section on series is a very, very specific series, and it's called the geometric series. And a geometric series looks something like this, where you have a ratio, a common base, like 2 or 3 or 1/2 or whatever, 3 halves, right, to the first power, then to the second power, then the third power, then the fourth power. So these exponents are what's increasing with every term in the sequence. So it looks like something like this. Now, a geometric series is actually really nice to look at. It is very, very specific. It's really nice because it's very easy to tell if it's divergent or convergent. And if it's convergent, I can actually find out what it adds up to be. So what makes a geometric series divergent? Well, let's take a look at an example. An example over here might be the series of, maybe there's a 2 here, and maybe there's a 3 halves to the n minus 1. Okay, this is some sort of a geometric series because the exponent is the only thing that's increasing with every term. So in this case, when I plug in 1, I get 2 times 3 halves to the 0 power, plus 2, and when I plug in 2, n equals 2, I get 2 times 3 halves to the first power, plus 2 times 3 halves to the second power, plus 2 times 3 halves to the third power, plus 2 times 3 halves to the fourth power, and so forth and so forth. Now, if you take a look, it's very easy to tell whether this series is convergent or divergent, because when this R, this base, or what we call the common ratio, okay, when that common ratio is bigger than 1, notice what's happening. 3 halves times 3 halves times 3 halves times 3 halves is actually getting bigger and bigger and bigger. So each of these terms that I'm adding gets bigger and bigger and bigger and does not approach 0. So the terms in the sequence does not approach 0. So this was divergent by the divergence test. So if the common ratio, the absolute value of the common ratio is bigger than or equal to 1, then the series, the geometric series, is divergent. In the same way, if the common ratio is less than 1, then this same geometric series will be convergent. So if in this case, instead of 3 halves, I had 1 half, and 1 half here, and 1 half, 1 half, and 1 half. Notice as we move along in each of these terms, I get 1 half, half of a half of a half to the third power, half of a half of a half of a half. So each of these terms are getting smaller and smaller and smaller. Right? So not only in a geometric series do I know that if the common ratio, if this r, this base, is less than 1, will it converge? I also know that this will equal to the first term over 1 minus r. Now I'm going to write that out here. This is what I'm going to call it the first term, and that's found here when I plug in that first variable, n equals 1. Okay, and this right here, just to put some, is what we call the common ratio. So let's take a look at what that looks like. Let's look at an example. Our first example says, determine if the geometric series converges or diverges. So we already know this is geometric. Now again, to repeat myself, geometric series is a very particular series. If you know it's geometric, then you follow this one formula. Not all series are geometric. In this case, we know that it is. So we want to write it in somehow this form, right? We want to get it to here so that I can find this common ratio to see if it's convergent or divergent. So this is where it gets a little bit tricky. One of the tricky parts about it. We got to find our general term. Now, in finding the general term of a geometric series, don't start with the first one. That gets a little difficult. Maybe not even the second one. Somewhere in the middle, maybe here, maybe here. Pick something like that. So if you're looking at the third term, n is equal to 3, right? If you know that it's geometric, you also know that you have something to some exponent, and it's that exponent it's exponentially increasing. Now, what is exponentially increasing here? Well, I can already tell the denominator is exponentially increasing. This is 3 to the first power, 3 to the second power, 3 to the third power. I'm assuming the next one is 3 to the fourth power. So the bottom will be 3. This one is 3 to the second power, which is n minus 1. Okay. The top part, it looks like there's a 5, and this is 5 times 2. This is 5 times 2 times 2. 5 times 2 times 2 times 2. So the 2 is exponentially increasing. There is a 5. I'm multiplying it by some exponential of 2. So it's 5 times 2. This is 5 times 2 times 2. So this is 5 to the second power, right? Which is n minus 1. So 5 times 2 times 2 times another 2, and so forth. The last thing to deal with here is then the plus and the minus, the plus, minus, plus, minus. So I'm going to deal with that separately for the time being. So it starts with the positive, then flips to negative. If it's just negative 1 to the n, and I plug in n equals 1, it would start with a negative, because negative 1 to the first power is negative. So instead, I'm going to do to the n minus 1. From n equals 1, the first term, out to infinity. Now, I'm going to simplify this to look more like the geometric form. What I have here from n equals 1 to infinity, I have the 5 in the front. I have the 2/3 as a common base to an exponent of n minus 1. And then I also have a negative 1 to an exponent of n minus 1. So I'm going to bring that negative in. So now what I have is I have r equal to negative 2/3. I'm not going to look at this number. Don't get in the habit of looking at this number. Instead of calling it a, I'm going to call it the first term. because sometimes it gets a little tricky. Sometimes they start at n equals 0. Sometimes this is not always n minus 1. This is a negative 2/3 to the n power. And that gets a little complicated. So instead of doing that, instead of calling it a, or this number here, I'm going to call it the first term. So I'm going to drop in that n equals 1. So I have 1 minus 1 is 0. This becomes 1, and I get 5. Or in this case, I can look straight up here. If I'm already given the first term, a sub 1 is 5. So if we take a look here, the common ratio, the absolute of the common ratio negative 2/3 is less than 1. So this definitely converges. What does it converge to? It converges to the first term over 1 minus the common ratio. So it will converge to 5 over 1 plus 2/3. So this becomes 3/3, and I get 5 over 5/3. It will converge to 3. So if I add up, add, subtract, and I keep going forever and ever and ever, this will actually add up to 3. Let's take a look at this next example. You got to determine if this geometric series converges or diverges. Now, we want this to look like a to the r to the n minus 1 from n equals 1 to infinity. This is the first term, second term, third term, fourth term. Now, in order to see exponents, I don't really like these decimals, so I'm going to change it. I'm going to change it to 10 minus 2 plus, this is 4/10. This is 8/100. Now I'm already starting to see some sort of an exponential growth in each term. So if that's the case, here we go. Again, I'm not going to choose one of these two. I'm going to try, maybe I'll choose this one because it's nice and positive, somewhere in the middle. I have 10 to the first power, 10 to the second power. Maybe this is 10 to the 0 power, which is just 1. So the denominator is going to be 10 to the first power, so 10 to the n minus 2. In the numerator, I have 2, 4, 8, 16. It's probably something 2 to the second power, right? 2 to the squared is what I want, so 2 to the n minus 1. The negative 1 is starting off positive, so it'll also be n minus 1. So now take a look at what we've got. Let's try it. If I plug in n equals 1, see what happens. N is equal to 1, this is 1, and this is 1. And we have 10 to the negative 1, which moves on up to be 10. So this looks correct. However, we have to rewrite it in this sort of form. We want one common ratio of r where the exponent is increasing. Right now we have 3 that we have to combine. So it looks like the numerators will be easy. It'll be negative 2 to the n minus 1. The denominator is an n minus 2, however. So how do I change that? Well, I want it to be n minus 1. And n minus 2 is basically n minus 1 minus a 1, right? So then that will give me negative 2 to the n minus 1 on top. Now remember how to split these. If I'm subtracting or adding a negative, it'll be 10 to the negative 1 times 10 to the n minus 1, right? So going backwards, just doing a little check. If it has a common base, I add the exponents, so I get negative 1 plus n minus 1, which gives me n minus 2. Now that means all I have to do is do one more step, and I move this 10 to the negative 1 up to the top. I get 10 times negative 2 over 10 to the n minus 1, because I combined this negative 2 with divided by this 10 from n equals 1 to infinity. So does this series converge or diverge? It looks like the absolute value of that ratio is less than 1, so this one converges. It converges to the first term, which again I'm going to look here, 10 over 1 minus the common ratio, right? So it converges to 10 over 6/5, 6/5. So 50 over 6.